We're now going to talk about properties of continuity. And these properties are very similar to the rules that we used to evaluate limits. And in fact, they are connected to those rules. So basically, if f of x and g of x are both continuous at C, then the following are also continuous at C here. The sum of f of x and g of x will be continuous at C. The difference will be continuous at C. A constant times one of the functions there is continuous at C. The product of the two functions is continuous at C. The quotient of the two functions is continuous at C, provided here that the bottom function is not equal to 0 at C. If I take the function and raise it to a power, it'll be continuous at C, given that this is an integer power, or the nth root of the function will be continuous at C, given that this is an integer, and then you also have to be careful when n is even that the function here is positive at that point. And another one here that we didn't have for limits is that the composition of the two functions will also be continuous at C. Given that the two functions are continuous, the composition will also be continuous. And you can actually think of these here as special cases of that, right? So let me show you how these are related to those rules that we learned for limits here. So I'm going to do this by just proving the first one, okay? And you could probably prove some of the other ones after that. So basically, for f of x plus g of x to be continuous at C, what that would mean is that the limit of, as the limit of the sum there approaches C, it would have to be equal to f of C plus g of C. Okay, so this is just a combined function, making a new function, and for the new function to be equal or to be continuous, the limit of that new function at C has to be equal to that new function evaluated at C. Well, this is actually pretty easy to show given that we have those rules. So to show this, the limit of this sum as x approaches C will be equal to the limit as x approaches C of f of x plus the limit as x approaches C of g of x, right? That's the rule for the limit. That's the rules that we learned earlier. You can split a limit up over a sum. Well, what we're given here is that both f and g are continuous at C. So that means this here will be equal to f of C, right? Because f of x is continuous at C. And this here means g of x will be continuous at C. Okay, so given that rule for limits plus the definition of continuity, we get that this is equal to that, and therefore the sum is continuous at C. Okay, so it follows from those two things. So now let's use these here to discuss the continuity of the following functions. Okay, so this one is the composition of two functions, right? One of them is, we could think of one of those functions as being y equals x squared plus 5x, and one of those functions is just being the square root of x. So it's like you're putting this inside of that. And so if both of these are continuous, right, then this will be continuous. But we have to be careful because this is only defined for positive values, right? The square root. So I gotta make sure for this entire thing to be defined, I gotta restrict the domain for when these are positive. Okay. So in other words, when x squared plus 5x is greater than or equal to 0. Okay. So then I can pull out an x here, and then I get x plus 5. And sorry, this is a minus, so this is actually minus, and this is minus. So x minus 5 when this is greater than or equal to 0. Okay? So basically this is like a parabola that's actually going, this is kind of going down. It goes through the origin. So this is x equals 0 and x equals 5. Okay, this is when they're equal, those are when they're equal to 0, right? Those are the two roots. And it's going to be positive because it's a face-up parabola. It'll be positive for negative infinity to 0, including the 0, and from 5 to, including the 5, to positive infinity. So in other words, if we're going to place this underneath there, it will have to be only on these intervals. So that'll be kind of the new domain. We can say that this is the domain of this. And the inside function is continuous there, and the outside function is continuous there. We just have to be careful at those endpoints, but as long as we say at the endpoints it only has to have the one-sided limit, we should be good. So then this thing will be continuous on this domain here. Okay? And so that would be the continuity of that function. So this one here, I just put a similar one here, except this here, this inside function, think of this as being a parabola that's shifted over, right, so this is like y equals x squared, and then I'm shifting it over 2, but I'm also raising it up 1, so this is my new vertex, and this is a parabola that comes down. Right? So this is a parabola that's always positive. So in other words, from negative infinity to infinity, this parabola here will always be positive. And so the domain here, I don't have any problems underneath the radical. The domain here is negative infinity to infinity for this, and it's going to be continuous at every point. Okay, because it's the root of this function. This function is continuous at every point, and the square root is continuous when this is positive. And so this is basically continuous at every point, okay, in its domain. So what about this? The cosine of the tangent of x, right? So the inside function is the tangent of x, and then the outside function is like the cosine of x. And we have no problem here. The cosine x will always be continuous. Okay? But this tangent here, if you remember, if this is like pi over 2 and negative pi over 2, at pi over 2, this thing goes off into infinity and negative infinity. Okay? At these two. So at pi over 2, it's going off to positive infinity. And so what's going to happen is this thing's going to oscillate up and down. So the problem here is that this function is not continuous at these points here. Okay? And so, so the composition won't be continuous at those points. And this is kind of a neat one to graph. I was playing around with different things. I'll graph the cosine of the tangent of x. And then maybe I'll do a trig window. And so what you see here is you see this little craziness going on at these different points, and you can be sure that where this craziness occurs is at the like the pi over 2 at the asymptotes of tangent. And if you zoom in on those, they will oscillate up and down forever. Okay? But if I consider this for just this interval, and I don't worry about those endpoints, so in other words, let's say I restrict the domain of this function here to negative pi over 2 to pi over 2, and I don't include those endpoints, Well, on here, tangent of x is continuous at every given point. Okay, so even though as you go close to them, it'll oscillate up and down, if I'm not equal to pi over 2, if I'm just a little bit before pi over 2, it might have oscillated a lot, but at that point, it does contain a limit. Okay, it will contain a limit. It's just at pi over 2, as you get closer and closer, it just keeps oscillating. But if you're just a hair away from it, it'll contain a limit. So any pair here, this is continuous, and so the composition here of the two functions will be continuous. So on this interval, the composition is continuous, and any interval like this, so like pi over, so if I do pi over 2 to 3 pi over 2, for example, and it's an open interval, it'll be continuous there as well. And then I could keep dot, 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 dot. For each one of these, this function is continuous, okay? But at those asymptote points, it will not be continuous, okay? But given that I restrict it to an open interval here, not including the endpoints, the composition of two continuous functions is continuous. And tangent is continuous, cosine is continuous. So, now this one is this is a neat graph. Let me graph this. So I'm going to go to my math menu, and I'm going to go to number, and I'm going to hit 1 for absolute value. And now I'm going to do, on top it'll be x sine of x, okay, divided by x squared plus 2. Okay, so this is, and I can zoom in here. So I'm going to put in this function here. And so let's graph. I'll graph it on a trig window. Okay, and we can do better than this because it's also flat around the axis. So the y min and y max, let me do -1 to 1. Okay, and I'll graph it there. And we can probably do even better here. Let me do y min at 0, because of course the absolute value is never negative, and it looks like this only needs to go up to like maybe 0.5. So it's kind of a neat function. If you notice at each of these points, because of the absolute value, basically without the absolute value, I think, see, this is going like this, and then this would have been, this here would have been negative, so it would have gone down, and that would have been positive, the next one would have been negative, okay? So these are actually sharp turns, but they're still continuous, right? They go down, the limit is equal to the same thing, okay? And it's just going, starting again and going positive each time. And those little mounds are getting smaller as you go down. And so basically you have this function, and this underneath is making them smaller as you go out. Okay, but the point here of looking at this graph is it looks like if it just keeps going up and down, getting smaller and smaller, this thing is always continuous. It doesn't have any breaks or holes or anything. And so we can see this now if we use our rules, right? So we got this outside function that's like absolute value of whatever you put inside, and then inside of that you have this x sine x over x squared plus 2, right? So the absolute value function is continuous. It has that sharp turn, right? It goes down and then goes up. And this is y equals absolute value of x. We haven't seen a lot of those, but this is actually continuous at all points. So we got a continuous function here. Now let's look at this. Okay, this is never 0. Okay, because x squared is always positive plus 2. So you never have any problem in the denominator. The function on the bottom is always positive. And this function never has any problem, okay, because x and sine x are both continuous, and so the product of them are continuous, okay. This is always continuous and never 0, so the quotient is continuous. So this thing will always be continuous, and we're putting that inside an absolute value, which is always continuous. So this thing is continuous on negative infinity to infinity, every place it's defined. Even though it's kind of weird with absolute values and a denominator and things like that, it ends up always being continuous, and it ends up being these little mounds that keep getting smaller and smaller as you go out. So that's kind of a neat function. Okay, so this is basically using those properties of continuity to determine exactly when a function is going to be continuous, when it's going to have problems. And so it's kind of a useful tool. Now there's one more thing I want to show you here that's a useful thing about continuity, and that is a theorem that talks about the limit of continuous functions. And I'm not going to prove this here, but basically if f of x is continuous at c, and I think I should say if f of x is continuous in general over the whole domain, or I should say if f of x is continuous at this limit here is what it should be, not just at c. So let me just erase this. If f of x is just a continuous function like sine of x or a polynomial or something else that's continuous, and the limit as x approaches c of g of x, if that exists, then basically you can take the limit in and out of f, in and out of the function, right? The limit as x approaches c of f of x, composed with g of x here, is equal to the function, and you're bringing the limit inside the function evaluated at the limit of g of x, okay? So it's basically, if you're finding a limit, you have a composition of functions, and you know f of x is continuous, right? Well, I could just, if it's continuous, I could just put the limit inside and just take the limit of the inside function, and then evaluate it at f, and then I'm going to get the limit of the composition of the functions. So a very, very nice theorem for finding limits. And the f doesn't actually have to be continuous everywhere. It just has to be continuous at the point that you're interested in. And so it's basically f would have to be continuous at the limit of g of x as g of x approaches c. Okay, that's where it would have to be continuous. But if it's continuous everywhere, then you're good to go. So I just have a quick example to show you how this could be useful in finding limits here. So I got this, the limit of cosine of some crazy thing, right? Now I can't just plug in 2 here because this would be undefined. Here, I'd get a 0 in the denominator. But what I can do is I can say this is equal to the cosine of the limit as x approaches c of x squared minus 4 over x minus 2. Okay, so in other words, I can put that limit inside and just take the limit here and then evaluate it at cosine, right? So I get the cosine of, this would be the limit, and this isn't c, by the way, this is 2. My c is 2. The limit as x approaches 2 of this, so I can factor this, right? And then of course this ends up canceling out like that, and so I would get the limit as cosine of, and the limit as x approaches 2 of x plus 2, right? And of course I can now take that limit, and that limit is just equal to 4, so this would just be the cosine of 4, whatever that is, okay? And I could plug it in. It would be, I'll just go ahead and do it, make sure I'm in radians, assuming that this is radians. Cosine of 4, and it'd be like negative 0.65, negative 0.654 if you round to 3 decimal places, and assuming that this is in radians. Okay, but the point here is this will allow you to find limits you haven't been able to find so far. In order to put this inside the function, continuity is what you need. It's not enough just for limits here. You got to know that cosine is continuous, okay, at that point, and then you can put this limit inside. Just take the limit of the inside and find the overall limit. So that's a nice rule.